Check out this camera angle. What do you think? You can see a lot of board. All right, so multivariable chain rule. We will use this. We'll use it all semester because we're going to have the world to come is going to involve substitutions. We're going to have to parameterize. We're going to parameterize a surface. So instead of having just the surface being z equals 9 minus x squared minus y squared, we're going to rewrite it as a parameterized surface in two variables. And so that means that x will be substituted by a function of, say, theta and r, and y will be substituted with a theta and r animal. And we get a completely different version of the same surface, just like when we parameterized a curve. Same curve, but it happens differently. And we have a parameter version different from the original one. Anyway, that's in the future. So we got to be able to take derivatives when we have substitutions like the parameterization that we did. So here's what's going on. It's actually a good thing. This chain rule thing's a good thing. We'll show you what it's saving you in a minute. So here's what we're starting with. This is your starter set. You have a function of x and y, but x is itself a function of s and t. Y is a function of s and t, but there's actually no s. But what we're saying is that x and y have their own domain of s and t, which makes f, technically, a function of s and t. So we can take the partial of f with respect to t. But here's what we're saving. I don't have to plug these in for every letter x and this for that y, and then do the partial with respect to x and the partial with respect to partial with respect to t. But we could. But here's what it's equal to. Partial of f with respect to x times the partial of x with respect to t. Because x has a t in its function. And then partial of f with respect to y, partial of y with respect to t. Y has a t in its function. So this whole thing is equal to the partial of f with respect to x, which is sine y plus 2x. That gets multiplied by the partial of x with respect to t, which is just an s. So we are allowing this, x's and s's, to play together. Because if somebody put a gun to my head, I could substitute in for that x, s times t. I could substitute in for that y, t squared. And I have all s and t stuff if I wanted to. But I can leave it like this. The book has their answers like this. Because you're one step away of having this form where everything's s and t. So you don't have to write it all out. So plus, and I'm up to this stage now. Partial of f with respect to y, well, that's just x cosine y. And then that's times the partial of y with respect to t, which is 2t. So I'm going to leave it to you to do these substitutions if you want to into here, and then do directly the partial of f with respect to t. And to see it matches this, you have to rewrite this with only s and t stuff. So you got to substitute into here. I'm trying to convince you that this is a lot less writing. It's quick, it's fast and easy. This is great. I hope I'm selling you on this idea. So let's do another one with these same two setups. Obviously, the next one to do is the partial of f with respect to s. So here's where you get to save work. One of these things is going to be a 0. Because the partial of y with respect to s is 0. So this whole term is gone. That's nice when it happens. So the answer for this one is the partial of f with respect to, my fault, y. No, this is x. This is x. I'm wrong. My fault. The y stuff's over here. So partial of f with respect to x, the same thing I had before. Partial of f with respect to x is sine y plus 2x. And now it's times the partial of x with respect to s, which is a t. And we are done. Just leave it like that. Isn't that fun? So chain rule is easy. Now the book does with multiple layers. This is only 2 layers. They do examples with 3 layers. And it is what you think it would be. The big idea is this. You follow the contributors. So for instance, y doesn't have an s here. So y doesn't contribute to this. Or you can do it all the way out, and you'll get a 0 for this factor, which makes this whole term 0. You get this the same thing as if you wrote all those things. But one of the things you can do is save work. There is no contribution from y through the variable s. Or let me say it better. There's no contribution for s through the variable y. So there's no partial of y with respect to s piece. So you got to think about it like that. All right, let's try. All right, so the only other concept we did today was introducing gradient. That's next. All right, we get a new operator. The symbol is this upside down triangle, and it operates on a scalar function, but a multivariable domain. And here's how it works. If you have f, a function of x, y, z, let's say, then the gradient of f is a vector. It's a vector, and the first coordinate is the partial of f with respect to x. The second coordinate is the partial of f with respect to y. The third coordinate is partial of x with respect to z. So in other words, the order here is the order of partials here. That's all you have to do. Isn't that great? So to do the gradient of this f, so here's our first example. I went to a two-dimensional domain, r theta. So this is my function of r and theta. Grad f, you write that bracket for vector, and you take the partial with respect to r. So that's going to be sine theta plus cosine theta, comma. Now you take the partial with respect to theta. So that's going to be r cosine theta minus r sine theta. I hope you see it. And that's it for gradient. That's how you do it. Now it has a bunch of properties which we didn't get to. We just barely had time to actually do a gradient or two. But we're going to get to the properties on Tuesday. The homework is just try some more tangent plane problems and be able to do some chain rule problems. So we aren't actually in the section with gradient yet. I just barely got a chance to introduce it, but I had enough time to make the speech about, hey, let's see what operators we have. The integral is an operator. The derivative operator we've seen and used a lot. We got the new partial operator, partial derivative operator, and now this guy here is actually interesting because in this spot we park a multivariable thing. In this spot we park a multivariable thing, but in this spot we have to have regular old f of x, and in this spot regular old f of x. So if you look at this, that's calc 1 and 2, these guys. Calc 3, these guys. Where you park in the operator position a scalar function with a multivariable domain. So that's the big deal with these guys. So that's the new operators that we've got. Partial derivative operator and gradient operator. So that's where we are. See you later.